3.8 Lesson 1, Applications of Sine and Cosine Derivatives. Our objectives for today are: 1. You will know how f of theta is equal to sine theta and g of theta is equal to cosine theta are defined using the unit circle. 2. You will be able to sketch the graphs of the parent sine and cosine functions. And 3. You'll be able to sketch graphs of functions that are transformations of the parent sine and cosine functions. So vocabulary, unit circle, we have parameters that can transform parent functions to give us, for example, a vertical translation of a parent function, a horizontal translation of a parent function, a vertical stretch or compression, or a horizontal stretch or compression of a parent function. So we have parameters that will give us transformations of parent functions, and we talked about some of the transformations that we'll be seeing. So for the parent functions, we want to note something called the period of the sine function or the cosine function, as well as the amplitude of the parent sine and cosine functions. When we talk about vertical translations, we'll be using the vocabulary midline axis or sinusoidal axis. When we talk about a horizontal translation, we will be using the vocabulary phase displacement. So now we will briefly review Objective 1, how the sine and cosine functions are defined using the unit circle, and then from that we will be able to sketch the graphs of the parent sine and cosine functions. So we have an angle of rotation with the initial side along the positive x-axis, and if we rotate counterclockwise, we will get a positive angle of rotation having a measure of theta radians. The terminal side of the angle will intercept a point on the unit circle, and the coordinates of that point will be generally x comma y. Now you can see that for certain angles we have the coordinates of the point on the circle. But generally it will intercept a point on the unit circle with coordinates x, y. How do we define sine of an angle theta? Sine of an angle theta is the y coordinate of the intercepted point, and cosine of an angle theta is the x-coordinate of the intercepted point. So that's how the sine and the cosine functions are defined using the unit circle. Using those definitions, we can come up with a table of values for both sine and cosine. So I can have input values that are angles of rotation and output values that are sine values. I can have input values that are angles of rotation and output values that are cosine values. So I'm going to work with some angles that are easy to work with, and these are called the quadrant angles. 0 radians, pi over 2 radians, pi radians, 3 pi over 2 radians, and 2 pi radians. These are called the quadrant angles. 0, pi over 2, pi, 3 pi over 2, and 2 pi. It's easy to work with these angles because these four angles, they intercept points on the unit circle with coordinates that are easy to remember. 1, 0 here, 0, 1, negative 1, 0, and 0, negative 1. And for sine, you're looking at the y coordinate of the intercepted point. So for the angle 0 radians, sine of 0 would be 0. For the angle of rotation pi over 2 radians, sine of pi over 2 will be 1. For the angle of rotation pi radians, sine of pi will be 0. For the angle of rotation 3 pi over 2 radians, sine of 3 pi over 2 will be negative 1. And for the angle of rotation 2 pi radians, the sine of 2 pi radians would be 0. And notice that after 2 pi radians, we are back at 0 radians. 2 pi and 0 are what we call coterminal angles. And one period of the sine function has been completed after going through 2 pi radians. And if you continue with another period, you're just going to cycle through these values again and again and again as you go through period after period after period. So the period of the sine function is 2 pi radians, and the range of the sine function, you can see that sine has a minimum value of -1 and a maximum value of +1. So that's the range of the sine function is from -1 to +1. And because the angle of rotation could be any real number, the domain of the sine function is all real numbers. So if I wanted to sketch one period of the sine wave, I can do that. And here you can look at my axes. I have my theta axis here, and the vertical axis would be f of theta. And I already have a scale for the horizontal axis. I can choose any scale I want for the vertical axis. For example, I could choose to make that 1, and this would be -1. And I would just plot my points. So I have 0, 0, which is right here. I have pi over 2, 1, which would be right here. I have pi 0, which would be here. 3 pi over 2, -1, which would be here. And 2 pi 0, which would be here. So this would be one cycle of the sine wave corresponding to one period of the sine function. So the period is 2 pi radians. We call this here the midline axis or the sinusoidal axis, and the distance from the midline axis to either a high point or a low point on the curve, we call that the amplitude. So the amplitude here would be 1. So we've looked at how the sine and the cosine functions are defined using the unit circle. And we've already sketched the graph of the parent sine function, and now we will sketch the graph of the parent cosine function before moving on to sketching graphs of functions that are transformations of the parent sine and cosine functions. So just like we did with the sine function, we will work in a similar way with the cosine function. So the definition of cosine of an angle of rotation theta using the unit circle is you look at the x-coordinate of the intercepted point on the unit circle. So we're going to work with the 4 quadrant angles: 0, pi over 2, pi, 3 pi over 2, and 2 pi radians. So cosine of 0 would be, the x-coordinate of the intercepted point would be 1. Cosine of pi over 2 would be 0. Cosine of pi would be -1. Cosine of 3 pi over 2 would be 0. And cosine of 2 pi would be 1. And just like with the sine function, the cosine function also has a period of 2 pi radians, and the range of the cosine function is from -1 to +1. And the domain of the cosine function is all real numbers. So if I want to sketch the graph of the cosine function, I will go ahead and do that. Let me go ahead and sketch the graph of the cosine function using a different color, and I'll write it down here. G of x is equal to cosine of theta. So on the same set of axes that I have the sine wave, one period of one cycle of the sine wave corresponding to one period of the sine function, I'll sketch one cycle of the cosine wave corresponding to one period of the cosine function. And I'll sketch it in blue so that it stands out from the green graph, which is for sine. So I have 0, 1, which is right here. I'm going to plot these points. I have pi over 2, 0, which is right here. I have pi -1. I have 3 pi over 2, 0. And I have 2 pi 1. So this is one cycle of This is one cycle of the cosine wave that you see here in blue. The period of the cosine function is 2 pi radians, and it also has an amplitude of 1. So now we've completed objectives 1 and 2, and we're ready to move on to objective 3. You'll be able to sketch graphs of functions that are transformations of the parent sine and the parent cosine functions. So let's take a look at the graph of the parent sine function once again. Now we're using the set of axes that you see here. This is the horizontal axis representing the angle of rotation, and this is the vertical axis representing the output from the function. So when we plot the points, we have 0, 0, we have pi over 2, 1, we have pi 0, we have 3 pi over 2 negative 1, and we have 2 pi 0. So this is one cycle of the sine wave corresponding to one period of the sine function, and of course the amplitude is 1. The distance between the midline axis and a high point or a low point here is 1. Now I can include additional cycles now that my axes are able to accommodate more cycles. And this would be, here you see 4 cycles of the parent sine wave corresponding to 4 periods of the sine function. So what we want to do now is we want to take a look at transformations of the parent sine function. So for example, suppose you have g of theta. Suppose you have g of theta is equal to 1 plus sine of theta. So what does this 1 do to the graph of the parent sine function? To understand how this parameter of 1 will have an impact on the graph of the parent sine function, think back to function notation. So when you look at number 1, the input for the sine function is theta, and the output from the sine function is sine of theta. So basically, when you look at number 2, you're adding 1 to the output from the parent sine function, or you're adding 1 to the y coordinates. I can write g of theta in terms of f of theta as follows. I can write g of theta is equal to 1 plus sine of theta, which is f of theta. So you're taking the graph of the parent sine function and you're shifting it by 1 unit, because what's going on is these are y coordinates from the parent function, and you're adding 1 to each y coordinate, causing each y coordinate to increase by 1. So take a look here. If I were to change this table from f of theta to g of theta, each of these coordinates will increase by 1 because I'm adding 1 to outputs from the parent sine function. So this will become 1, this will become 2, this will become 1, this will become 0, and this will become 1. And if I plot these points to get the graph of the function g, I have 0, 1. Let's do this graph in maybe blue ink. So 0, 1, pi over 2, 2, pi 1, 3 pi over 2, 0, and 2 pi 1. So here's one cycle of the graph of g. And you can see that it is the graph of the parent sine function shifted up by 1 unit. And here we can look at additional cycles of the graph. So there's the graph of g of theta. So this parameter of 1 had the impact of raising the graph of the parent function by 1 unit. It caused a vertical translation upward by 1 unit. So now we'd like to take a look at our third function. H of theta is equal to 3 times sine of theta. So when you have 3 times sine of theta, again, what's going on? What do you expect will happen to the graph of the parent sine function to give us the graph of h? To understand how the graph of the sine function will be transformed to give us the graph of h, once again, go back to function notation. So for number 1, we have f of theta is equal to sine theta. So we may replace the sine theta here with f of theta. So we have h of theta is equal to 3 times f of theta. And remember, in function notation, f of theta is the output from the function f. So h of theta takes outputs from the function f and multiplies by 3. Because what you have here, again, is sine of theta first and then multiplied by 3. So when you look at the table here for sine of theta, you have these outputs at the quadrant angles 0, pi over 2, pi, 3 pi over 2, and 2 pi. And now you're going to multiply 0, 1, 0, negative 1, and 0 by 3. And when you do that, this is what you get. So 0 times 3 is still 0. 1 times 3 is 3. 0 times 3 is still 0. Negative 1 times 3 is negative 3, and 0 times 3 is still 0. So now we're going to plot these ordered pairs, and we'll get the graph of h. So we have 0, 0, we have pi over 2, 3, we have pi 0, we have 3 pi over 2, negative 3, we have 2 pi 0. So when I connect these points, I get one cycle of the graph of the function h of theta, which is 3 times sine of theta, and you can see that we've had a vertical stretch of the parent sine graph. We've had a vertical stretch of the parent sine function's graph. And I can do additional cycles. And I can also do additional cycles to the left of the vertical axis. So this is the graph of h of theta is equal to 3 times f of theta. It gives you a vertical stretch by a factor of 3. Now we'd like to take a look at number 4. We have k of theta is equal to sine of 2 theta. Unlike number 3, in which we were multiplying the output from the parent function by 3, for the function k, something is being done to the input of the parent function. So this will have an impact on not the outputs from the parent function, but input values into the parent function. Notice the table that I just made. It has 3 column headings. The column in the middle is 2 theta, which matches what we call the argument of the sine function. So I'm adding this to our vocabulary list. What we're taking sine or cosine of, we call that quantity the argument of the sine function or the cosine function. It's what we're taking sine of or cosine of. So we have 2 theta as the argument of the function. We're taking sine of whatever 2 theta is. Again, it's easy to take sine of quadrant angles. So we want to set the argument equal to these quadrant angles. The argument is 2 theta, and we would like 2 theta to be 0, pi over 2, pi, 3 pi over 2, and 2 pi. Why? Because it's very easy for us to evaluate the sine function at these quadrant angles. So sine of 0 is 0 from the unit circle. We look at the y coordinates. Sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2 is negative 1. And sine of 2 pi is 0. But when you want to graph the function k of theta, you need ordered pairs that are theta for the input and k of theta for the output. So what you have in the middle column is not values for theta, but the values for 2 theta. So you need to solve these equations to figure out the corresponding theta values. So in the middle column, we have 2 theta is equal to 0. We have 2 theta is equal to pi over 2. We have 2 theta is equal to pi. We have 2 theta is equal to 3 pi over 2. And we have 2 theta is equal to 2 pi. So if you solve for each of these, if you solve each of these equations for theta, in the first one you get theta would be equal to 0. So you write 0 here. In the second one you get theta would be equal to pi over 4. Multiply both sides of this equation by 1/2 to get theta is equal to pi over 4. So you write that here. In the third equation, multiply both sides of the equation by 1/2 to get theta is equal to pi over 2. In the fourth equation, multiply both sides of the equation by 1/2 to get theta is equal to 3 pi over 4. And in the fifth equation, multiply both sides of the equation by 1/2 to get theta is equal to pi. So this will give us the ordered pairs that we need to graph our function for number 4. Our ordered pairs are going to be, you look at theta and k of theta. So our ordered pairs are going to be 0, 0. I'll go ahead and plot the point, 0, 0. Pi over 4, 1. So pi over 4, 1 would be right here. Pi over 2, 0, which would be right here. And then 3 pi over 4, negative 1. And then pi 0. So when I sketch one cycle of the graph, this is what I have. And when you compare that to one cycle of the parent function's graph, you can see that there's been a horizontal compression. So the period of the parent function's graph was 2 pi. And the period of the function k is half of 2 pi. It's only 1 pi. So the period became 1 pi. So there's been a horizontal compression by a factor of 1/2. So if you want to figure out the period of a function such as this, you can look at the number that's multiplying theta. You can take the period of the parent sine function and divide by the number multiplying theta, and that will give you pi for the period of this function. So when you have a parameter such as the one that we have for number 4, and it has an impact on the input of the parent function, that will cause either a horizontal compression, as we see for number 4, or possibly a horizontal stretch if you have a value here that's between 0 and 1. But what we have here is 2, so we have a horizontal compression. If you had 1/2 there, it would be a horizontal stretch by a factor of 2, because 2 pi divided by 1/2 will give you 4 pi. So now we'll take a look at number 5, and then we'll do numbers 6 and 7 afterwards. So for number 5, you should make this observation. You should make the observation that we have sine of 2 theta here. For number 4, we had the function k of theta, and that was equal to sine of 2 theta. So in fact, for number 5, I can write r of theta is equal to 1 plus 3 times k of theta, because sine of 2 theta, that was the function that I had for number 4. And understanding function notation, here's what we need to do. K of theta is the output from the function k. And we're taking the output from the function k and multiplying by 3 and adding 1. So if I wanted to do a table of values for the function for number 5, I would do something like what we did for number 4. I would have 3 columns. The middle column will be 2 theta, which again is the argument of the function. And I want the argument to be the quadrant angles. And then I need to solve for what theta should be, the same way I did in number 4. And then for the last column, of course, it's now going to be labeled r of theta. And what do I need to do? Well, I need to take the output values from k of theta, multiply by 3, and add 1. And how did I get these output values for k of theta? I just evaluated the sine function at these values for the argument, which are really easy to do because these are quadrant angles. So this is what you need to do. So sine of, when 2 theta is 0, I have sine of 0, which is 0. 3 times 0 is 0, plus 1 is 1. When 2 theta is pi over 2, I have sine of pi over 2, which is 1. 3 times 1 is 3. 3 plus 1 is 4. So I write 4 here. And then when 2 pi is pi, I have sine of pi, which is 0. 3 times 0 is 0. 0 plus 1 is 1. And when 2 theta is 3 pi over 2, sine of 3 pi over 2 is negative 1. 3 times negative 1 is negative 3, plus 1 is negative 2. And when 2 theta is 2 pi, sine of 2 pi is 0. 3 times 0 is 0. 0 plus 1 is 1. So to sketch the graph for function number 5, I'm just going to take the ordered pairs from my table. And remember, you have to take the ordered pairs for theta and r of theta. So you take the ordered pairs 0, 1, and here is 0, 1, and then pi over 4, 4. So here is pi over 4, 4, and then pi over 2, 1, pi over 2, 1, 3 pi over 4, negative 2, 3 pi over 4, negative 2, and pi 1. So here we have one cycle of the graph for number 5. And you'll notice that a cycle is completed in a period of pi radians. So the period of this function is pi radians. You will also notice that the midline axis has moved. It has moved up by 1 unit. The midline axis now is the line y is equal to 1. That is the midline axis. And that's because of this 1 here, which caused a vertical translation upward from the graph of the parent function. Why is the period pi? Because of this 2 in the argument. So you take the period of the parent sine function and divide by the 2 that you see there, giving you pi for the period of the function for number 5. And the amplitude is 3. And why is the amplitude 3? The amplitude is 3 because of this parameter being 3. And you can see that the distance from the midline axis to a high point or a low point is, in fact, 3 units. That's our amplitude. The amplitude is 3. And you can see that I sketched another cycle of the graph for the function r of theta. Now we take a look at number 6. We have s of theta is equal to sine of theta minus pi over 4. So theta minus pi over 4 is the argument of the sine function for number 6. And let's make a table of values, and our table will have 3 columns. The middle column will be the argument. We're taking sine of whatever the argument is, and we know that it's easy to evaluate the sine function at these 4 quadrant angles. So we'd like the argument theta minus pi over 4 to be 0, pi over 2, pi, 3 pi over 2, and 2 pi. And what would be the output values from the function? What would be s of theta when the argument is 0, pi over 2, pi, 3 pi over 2, and 2 pi? Well, it's really easy to find sine of 0. Sine of 0 is the y-coordinate of the intercepted point, which is 0. Sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2 is -1. And sine of 2 pi is 0. But when we want to sketch the graph of the function s of theta, I need to find ordered pairs that are input and output. The input is not theta minus pi over 4. The input is just theta. Theta minus pi over 4 is the argument. So now I have to work backwards to figure out what inputs will give me the quadrant angles for the argument. But that's easy to do. All you do is you take theta minus pi over 4 and set that equal to 0 and solve for theta. Take theta minus pi over 4, set that equal to pi over 2 and solve for theta. Take theta minus pi over 4, set that equal to pi and solve for theta. Take theta minus pi over 4, set that equal to 3 pi over 2 and solve for theta. Take theta minus pi over 4, set that equal to 2 pi and solve for theta. So in the first case, add pi over 4 to both sides of the equation. You get theta is equal to pi over 4. So I'm going to write pi over 4 here. In the second case, add pi over 4 to both sides of the equation. You get pi over 2 plus pi over 4, which is 3 pi over 4. So I write 3 pi over 4 here. In the third case, I have theta is equal to pi plus pi over 4, which is 5 pi over 4. And I can write 5 pi over 4 here. And then in the next case, I have theta is equal to 3 pi over 2 plus pi over 4, which is going to give me 7 pi over 4. You might be noticing a pattern here with the numerators. I'm going from 1 pi to 3 pi to 5 pi to 7 pi, and this one will be 9 pi over 4. You get that by adding pi over 4 to 2 pi. 2 pi is, of course, 8 pi over 4, plus 1 pi over 4 is 9 pi over 4. So now, these are the ordered pairs that we need to plot. Input, output. Pi over 4, 0. 3 pi over 4, 1, and so on. And then I would have 5 pi over 4, 0, 7 pi over 4, -1, and 9 pi over 4, 0. And I've plotted those points in gold. And if I were to sketch the graph of s of theta, this is what I see. This is the graph of s of theta in gold. And you can compare that to the graph of the parent sine function, which you see in red. And you can see that what we have is what we call a phase displacement, or a phase shift, also called a horizontal translation to the right by pi over 4 units. And that's due to this parameter being pi over 4. And in a later lesson, we will assign letters for each of the parameters. So let's go ahead and sketch another period of the graph of s of theta. And there you have it. And I could continue sketching the graph to the left, and I would basically just see the same thing. It would be a phase shift of the red graph to the right by pi over 4 units. And you can see that I've done that just now. Now we want to take a look at how to graph the function t of theta. And one thing that I want you to notice about t of theta is the following. You can see here t of theta is equal to 1 plus 3 times sine of theta minus pi over 4. And of course, sine of theta minus pi over 4 is the function that we just graphed. It's the function s of theta. So we could write t of theta as 1 plus 3 times s of theta. And what this means is you would take outputs from the function s of theta, multiply each output by 3 and add 1 to get the corresponding outputs for the function t of theta. Or if you wanted to just work with the function as written here originally, you would make a table of values like we did for number 6. The argument of the sine function is theta minus pi over 4. So you would have your middle column with theta minus pi over 4 as the column heading. And you would choose the quadrant angles to be the argument. And then you would solve for theta the same way we did in number 6. And you would find that for each of these values for theta minus pi over 4, theta would be pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, and 9 pi over 4, respectively. And then the last column will, of course, now be for t of theta. And what are you going to do? You're just going to evaluate the sine function at each of these argument values as you have in the middle column, because sine is evaluated at the argument, which is theta minus pi over 4, and then you will multiply the output from the sine function by 3 and add 1. So let's go ahead and do that. So when the argument is 0, sine of 0 is 0, and then you have 3 times 0 is 0, plus 1 is 1. When the argument of the sine function is pi over 2, sine of pi over 2 is 1. 3 times 1 is 3, plus 1 is 4. When the argument of the sine function is pi, sine of pi is 0. 3 times 0 is 0, plus 1 is 1. When the argument of the sine function is 3 pi over 2, sine of 3 pi over 2 is negative 1. 3 times negative 1 is negative 3, plus 1 is negative 2. And when the argument of the sine function is 2 pi, sine of 2 pi is 0. 3 times 0 is 0, plus 1 is 1. So now to sketch the graph of the function t of theta, I need ordered pairs input and output, theta and t of theta, and my ordered pairs will be pi over 4, 1, 3 pi over 4, 4, 5 pi over 4, 1, and so on. So I'll plot pi over 4, 1, which is right here, and then I will plot 3 pi over 4, 4, which is right here, and then I have 5 pi over 4, 1, and then I have 7 pi over 4, negative 2, 7 pi over 4, negative 2, and then I have 9 pi over 4, positive 1. So when I connect these 5 points with a smooth curve, this is the graph that I get for the function t of theta. And we have one cycle of the graph. And we want to make some observations about how this compares to the graph of the parent function f of theta is equal to sine of theta. So the first observation that you want to make is that because of this parameter pi over 4 in the argument, you have a horizontal translation to the right by pi over 4 units from the graph of the parent function, or we call that a phase displacement or a phase shift to the right by pi over 4. And because of this parameter being 3, the amplitude of the parent function was 1, and the amplitude of our function for number 7 is 3. And again, the amplitude is the distance from what we call the midline axis, which is halfway between the high and the low points, and either a high point or a low point. So this is the amplitude. The amplitude is 3. And that has to do with this parameter 3. And then you can see that the midline axis has the equation y is equal to 1. The parent function's midline axis has the equation y is equal to 0. So the midline axis has been shifted up by 1 unit, and that is because of the parameter 1 that we have here. And again, in a later lesson, we will be assigning letters for each of these parameters. So here we have the graph of t of theta in blue. One period of the function is represented by one cycle of the graph. And the period is 2 pi radians. You can get the period by taking 9 pi over 4 and subtracting pi over 4. You get 2 pi radians. And I just added one cycle of the graph to the right, and I could add additional cycles to the left as well. And there you see the graph of t of theta in blue. So today we looked at how the parent functions sine and cosine are defined using the unit circle. We looked at the graphs of the parent functions for the sine and cosine functions, and we looked at several examples for sketching the graphs of functions that are transformations of the parent sine and cosine functions. We used the word parameters. A parameter determines a particular transformation, and we will be assigning letters to the parameters in the next lesson.